Hey there, all right, welcome back. And now we're going to take a look at how we use this concept of vector components within the context of force problems. So we're going to start off with a couple a little bit easier ones, and then I think the third one is a little bit more of that, vectors at an angle and all that kind of stuff. So starting off a little bit easier. But if you don't have that list of steps from the last video, like how to do these vector components at angles things, you may want to have your little post-it note with your kind of cheat sheet of steps to do on there, because it definitely does help a little bit. So let's take a look at a practice problem. Here we've got you're taking your cat for a walk and you're applying a force of 25 newtons at an angle of 50 degrees above horizontal. What are the X and Y components of this force? So this is just kind of a warm up to get us going into our next problem. But let's take a look at how we would diagram this problem and how we would figure out what our X and Y forces are. So if we have our cat, there it is, there's our cat right there, and we're applying a force to it, right? There's FA. Again, why you never take a cat for a walk. So we know some things about what's happening in this particular system. For example, we know that the force itself is equal to 25 newtons. Again, this is at the angle. Sorry, that looks a little funky. I don't have great handwriting with this. 25 newtons, there we go. And we also know that it's at an angle of 50 degrees. Again, now 50 degrees above horizontal. So that means that our angle in here, like this angle, is 50 degrees. So the question is asking you, what are the X and Y components of that force? So if we take a look at our diagram over here, we actually have an X component, an over, and a Y component, an up, if you want to think of it that way. So if we want to, I'm going to use two different letters to abbreviate these. This one here would be FAX. Because I can do a lighter color for that, but FAX, it's the X component of the applied force. The other one, this direction, would be the FAY, right? It's the Y component of the applied force. So you'll see this sort of abbreviation or this sort of notation pretty regularly, as opposed to just calling it X and Y. Now we're talking about the X component of the force and the Y component of the force. So a lot of times we'll do that, or FX, FY is fine. So what are our X and Y components? Well, this is simply using SOHCAHTOA. So when we're trying to look at FAX, for example, or FAY, since I still have my red pen, FAY, this one right here, well, what do we know about this? We know the angle, we've got the hypotenuse, and FAY is the opposite side of the triangle. So therefore, we are going to use sine, because sine is SOH, right? Sine of 50 degrees is equal to the opposite over the hypotenuse, right? We're using SOH is the one that we're using right now. So sine of 50 is equal to the opposite side. Well, the opposite side is FAY. That's the Y component of our applied force, divided by, well, the hypotenuse, which is just FA, also known as 25 newtons. So this is now just math. The sine of 50 degrees times 25 newtons gives me an FAY equal to, again, we're doing two digits here. We're going to call it 19 newtons. Again, that's FAY. In other words, there's an upward force of about 19 newtons. Okay, well, how about FAX? The X component of this, I guess I was using blue, huh? So FAX, I don't like to, that's hard to read. My apologies. Let me get a lighter color. Let's try this one. I like that one better. Okay. So we're going to do FAX. FAX is, well, FAX is adjacent to the angle. Because it's adjacent, we have to use one of these guys, right? It's the adjacent side. So this is this is cosine. If you use sine for one side, you're going to use cosine for the other side. That's pretty easy. So cosine of 50 degrees is equal to FAX over 25 newtons. Again, the X component is adjacent, and the 25 newtons is FA. It's the hypotenuse. So cosine of 50 times 25. And again, you get pretty good at saying, well, I use sine for one, it's got to be cosine for the other one. So in this particular case, it is 16.06 something or other, so 16 newtons. In other words, as I'm pulling my cat across the floor with a force of 25 newtons, about 16 newtons of force is being used to pull him horizontally, and about 19 newtons of force is the vertical component, basically just me bending over and dragging him across the floor. So I think we're going to use these in our next bit. So that's our X and Y components. This one here is equal to Y, and this one here was equal to X. All right, so let's take a look at what we've got going on here. Same cat, well, different cat in the picture, but same idea. You apply a force of 25 newtons at an angle of 50 degrees, the same one that we did before. What will be the cat's acceleration? So I'm going to quickly resketch my little drawing here. Again, here's my cat. Here's my applied force, Fa, right? Here is my Fax and Fay, Fay, Fax. We knew that this one was 25 newtons. And then we figured out, let me go back and look really quick, which one is 16 and which one's 19. The Y is 19 and the X is 16. So this one right here was equal to 16 newtons, and the Y here was equal to 19 newtons. Again, we figured that out on the previous page. Okay, so this question is asking us about the cat's acceleration. Cat's acceleration. Well, if we're talking about acceleration, that means that we have to be using Newton's second law. Net force equals mass times acceleration. So we've got the mass of the cat, so we can plug that in. We're solving for acceleration, that's fine. So what's net force? Okay, so here's the important part about this. What if this is net force? It turns out when we're applying forces at angles, when we're dragging something across the floor, it's only, and this is the important part, only the component of the force that is actually in line with the movement is what's doing the work. So only in this particular case, the X component is adding to acceleration, is used for acceleration. Okay, well, why is this? Well, if the cat's accelerating horizontal, I'm assuming you're not jerking the poor cat off the floor. I'm assuming you're just dragging him across the floor, okay? If you're lifting the cat off the floor, you are not a nice person. So if our cat is literally moving this direction, that's his direction of movement, and our acceleration is that direction, then we can only use the force that is in that direction, which means that it's got to be F-A-X. Sorry, now I almost wrote Y there. It's only the F-A-X that's contributing to the acceleration of the cat. Again, it's the parallel forces. So if it's accelerating horizontally, it's only the horizontal version of that force that's actually helping. The vertical part is just so you don't hurt your back. That's really what it comes down to in this particular case. If the object was moving vertically, then the only force that we would be worried about would be the vertical force, or F-A-Y. So in this case, our net force is going to be equal to, well, it's the only force that's on there, F-A-X. That's the only force that we have that's working in the horizontal direction. We're going to ignore friction for right now, which equals to M times A. So again, that's the big idea with this. Now that we've figured out what it is, we know that 16 newtons is equal to 5 kilograms times its acceleration, and then we can just divide. So 16 divided by 5 is our final answer, which ends up being 3.2 is this poor cat's acceleration. 3.2 meters per second is the acceleration of the cat as we're dragging his little sorry furry butt across the floor. So again, the big takeaway, we use X and Y components to determine which parts of a force at an angle are actually contributing to the acceleration of that. And they have to be in the same plane. So if it's moving horizontally, then only the horizontal force. If it's moving vertically, then you only use the vertical force. So that's the kind of big takeaway from this. All right, here's our last one here. This is going to be one of those forces at an angle a little bit longer. We've got two dogs here playing tug. We've got one's pulling up and then one's pulling down. We want to know what the net force is on the toy. We need to know the number, which is the magnitude, the direction, the angle. So this is going to be one of those longer ones. So you might want to hit pause and get your list of hints, whatever you got. So here's our tug toy right here. There's our toy right there. We've got two forces on it. Spike is pulling right and up with a 12 Newton force at 20 degrees. Okay, so there's my imaginary horizontal. To the right and up, that's this way, okay, at 20 degrees. And it looks like 12 newtons of force. So that's one applied force. The other one is pulling to the left and down. Okay, so the left and down with a 57 Newton force at 10 degrees. Yikes, okay. So there's my horizontal. 10 degrees, something like that. This would be 10 degrees. And this is 57 newtons. Okay, again, we've got our two different forces that's on here. We got pulling down and to the left and up and to the right at slightly different angles. I know my drawing here looks like they may be parallel. They're not. Again, 20 degrees and 10 degrees. This one's almost horizontal. What's the net force on the toy? This means that we need to figure out our net force. We have to figure out our sum of our x's, and we have to figure out a sum of our y's, and we're going to use those then to figure out what our resultant is. That's what we're trying to do. How do these add together? Now they're going opposite directions, so we have to really keep track of our negative signs on this. This is going to be important for what we are up to. All right, so let's use our light blue here. We'll use our light blue here for spikes. I guess we'll use spikes in light blue like that. And then we can use a different color for Bonzo, whatever, right? Bonzo. We'll use green for Bonzo when we're ready to go with this one, just to help good on that one. Okay, so take a look at spike. Okay, here's spike's vector. It is 12 newtons. It's at 20 degrees. So let's find out the x and y components of spike. So this is F of S for spike. So we know that we have F, S, X, and F, S, Y. Okay, use our vector components to figure out what these are. So here's spike's different pieces. So in terms of this, the opposite side is going to be the y component, and the adjacent side is the x component. So we're going to do the x components. I'm going to do my x component here, and I'll do my y component over here. So for this, for the y, or for the x component, this is the adjacent side. So this is going to be the cosine of 20 degrees equals, let's see, it's opposite, or sorry, it's adjacent over hypotenuse, right? Adjacent is F, S, X over our hypotenuse, which is 12. So cosine of 20 times 12, cosine of 20 times 12 is equal to, again, we'll do this with two digits. It's 11.27. So we'll call it 11 newtons. So 11 newtons equals F, S, X. Okay, for our y component now, this is going to be the opposite side. So this is going to be the sine of 20 is equal to F, S, Y over 12. So sine of 20 degrees, why do I keep doing that, times 12 is equal to 4.104. So 4.1 equals F, S, Y. So now we got to think about directions. Let's use our typical this direction is positive. Let's call that, and we'll call that direction as positive. So in this particular case, these are both positive vectors. It's to the right 11 newtons, and it's up 4 newtons. So we're going to do that part. Now let's take a look at what's happening with Bonzo. So I'm going to switch colors over here to green, nice bright green here. So Bonzo's going the other way. Bonzo's going this direction. That's the direction that Bonzo's pulling, down and to the left. This is 57 newtons of force, and we know that its angle here is about 10 degrees. So again, with this, we're going to figure out what our x and y components are. So we've got F, Bonzo y component, and we've got the F, Bonzo x component. Our x component is cosine. Again, cosine is the adjacent one in this case. So now for Bonzo, cosine of 10, because that's our angle, equals FBX for Bonzo, divided by 10, right? No, 57 newtons. Wow, Bonzo's strong. 57 newtons. So cosine of 10 times 57 is a downward force, a horizontal force of 56 newtons equals force of Bonzo in the x direction. Again, that's 56. I'm going to do the same thing for the y component now. What's the vertical part of him? This is going to be the sine of, again, 10 degrees equals the Bonzo force in the y component divided by 57. Bonzo's super strong. Little dogs sometimes, they got a lot of viciousness to them. So the sine of 10 times 57 is equal to 9.89, so I'm going to call that 10. 10 newtons equals FBY. Let's take a look at our directions. Again, this is the part that students a lot of times forget to do. What directions are these going? Well, Bonzo is pulling to the left. The x component of this force is to the left. Therefore, this is negative. Bonzo's also pulling down. So this is negative. Okay, Spike was pulling up and to the right, so those are both positive. Bonzo's pulling down and to the left, so these are both negative. So again, we got to be a little bit careful with this. So now we have our two x components and our two y components. So what's our next step? Our next step is to figure out the sum of our x's and the sum of our y's, because now we can use Pythagorean theorem to figure out what these all are. So the sum of our x's and the sum of our y's. The sum of our x's are right here. Let me switch colors one more time. Here is the sum of our x's. There's this x, and then here's this x. So their sum of our x's is actually 11 minus 56, or 11 plus negative 56. So to find that the sum of our x's is equal to plus 11 and minus 56. That's how those two add up together. 56 minus 11 is a negative 45. Again, it's mostly down. It's only going, x left and right. To the right, it's going to the right 11, but it's going to the left 56. That means the net force is to the left 45. So that's what this is, our sum of our x's. For the sum of our y's, here they are right here. We've got 4.1 up, and we've got negative 10 down. So the sum of our y's is equal to 4.1 and negative 10. So 4.1 minus 10 is equal to negative 5.9. It's the sum of our y's. So I'm going to need to erase some of this work that's on here so I have some room to finish what our problem is. But now we know the sum of our x's is, and we know what the sum of our y's is. So now we can sketch this and take a look at it. Okay, I'm going to erase. Pardon me for doing this. I know it's like, no. Remember, you got a video. You can rewind. Okay, so here we go. We take a look at this. This means that pretty uniformly, our friend Bonzo here is winning, right? He's definitely winning this tug of war. Spike here is a big softie. Doesn't he look like a sweetie? Bonzo, though, the little dogs like that, like I said, they're vicious in a good way. I mean, in a bad way. Okay, so let's sketch a result and see if we can figure out what direction this thing is going. I'm going to use my nuclear green color. Now I'm going to use a nuclear, what color should I use? Red? Sure, why not? Use yellow. Okay, so what does this mean? So the sum of our x's is negative 45. Again, negative means to the left. And it's down 6, negative 5.9. That means that this right here is our resultant. Our resultant is going to the left and down, kind of in Bonzo's direction. He was winning this particular tug of war. So now, once we know what this is, now we can do Pythagorean theorem. 45 squared plus 5.9 squared, right, equals r squared. So just use your Pythagorean theorem that's on there. It is negative 45 squared plus negative 5.9 squared equals r squared. Pythagorean theorem. 45 squared plus 5.9 squared. I'm kind of cheating because I know that when you square negative numbers, they turn out just fine. They turn out positive. So that's that plus that squared. I guess got to take the square root of 2059. Second square root. And my answer, that means that r is equal to, it's 45.38 with 5. So the 2 sig figs is going to be 45 newtons. So this right here is 45 newtons. Again, that makes sense with sig figs. I know it's like, wait, wasn't that 45? Yeah, but 45 versus 6, it's not a very big angle, so that it's okay. If you do the squaring on there, it makes sense with sig figs. That's all right. And then the last part we need to do is our angle. So we've got to figure out what our angle is. Again, for our angles, we typically use tangent at the last side. Tangent of theta is equal to opposite over adjacent, which is equal to 5.9 over 45. In this case, these are directionals, the negative signs. You can leave them in there if you want to, or you can take them out, but it's to the left and down is really what that means. So if I do the inverse tangent of 5.9 divided by 45, it's going to be a small value. It's going to be like in that, not quite 10 range. And I get a value of that, 7.46. So theta is equal to 7.5, basically 7.46. 5 degrees. Now, what direction is that? That direction is down and to the left, or to the left and down, I guess is probably what I would end up saying. So this way right here, 7.5 degrees below horizontal to the left would work, something like that. So what is our resultant net force on the toy? Okay, our resultant force, we need a magnitude, we need an angle, and we need a direction. Our resultant is equal to 45 newtons at 7.5 degrees below left, horizontally, right? So it's kind of down and to the left. Doing left, right, up, down is always hard to do. So below, down, and to the left. So there you go. Dealing with vector components and adding these up. We know that our friend Bonzo here is quite bonzo and actually won that tug of war. So I hope this helped a little bit. I know that doing vector components is definitely sort of confusing when you're trying to figure out this. Again, you're trying to find your x's, you're trying to find your y's, then you use Pythagorean theorem and tangent to describe that final resultant vector. So there you go. And I will see you guys in class.